Welcome to Statistical Mechanics. This is a series of lectures designed to give you further understanding of statistical mechanics in the chemical context. Previously, in statistical mechanics, we were discussing about how statistical mechanics connects the microscopic and the macroscopic world. Remember that what we said is that statistical mechanics looks to individual molecules, atoms, and how is the collective behavior of these particles in the atomic world, and how does it connect to macroscopic properties like pressure or temperature that are those that we observed, that we measured, and that help us describe the macroscopic world. As we said, each regime of scales has to be described phenomenologically in terms of variables and laws that are observable in that regime. And we use statistical methods to describe how our molecules behave. We also refresh our mathematical knowledge on probability. We use the example of playing dice to get to the ideas of how to operate when we have two events that could happen simultaneously, so probability of A or B, and how the total probability is the addition of the individual probabilities, and how, on the other hand, if we have the probability of A and B, the total probability is the product of the individual probabilities. This will help later on in the course to apply probabilities when we are describing molecular systems. So at this point, and from the previous lecture, you should be familiar and know what is statistical mechanics in the context of physics and chemistry, and in relation to thermodynamics, with which you are already familiar. And we also have looked at some concept that would help you refresh your mathematical knowledge on probability. So let's continue then what we were discussing before about the four particles in two distinguishable bulbs, and how we can go from these four particles or four molecules into much more complex systems with much more number of particles, and how that gets more complicated, but simply or easy to describe using a statistical mechanics, using a statistical methods. Let's go back to the table that we saw about all the possible arrangements of four molecules in two distinguishable bulbs. These were all the possible scenarios where we go from 0 on the left side and 4 on the right side, up to 4 on the left side, 0 on the right side, and then we go through all the other possible combinations of A, B, C, D molecules in the 0, 4, 1, 3, 2, 2, 3, 1, and 4, 0 arrangements. Remember that the total number of possibilities was 16. Well, these 5 columns in this table are the 5 possible macro states or observations that we could have in our system. Now, each individual component of each of these 5 macrostates up to these 16 are microstates. So we have 16 microstates that are distributed in 5 macro states. Now, the importance of this, and why we are taking some time to really understand that, is that according to statistical mechanics, the most probable macrostate or observation is the one with the most microstates. This is a fundamental core concept that we need to remember because it's essential to our knowledge and understanding of the microscopic world. Based on that, you can clearly see that the arrangement in which you have 2 molecules on the left side and 2 molecules on the right side is the one with larger number of microstates, and therefore is indeed the one that we expected, in which the same number of molecules are distributed on both sides of our doubled bulbed bottle. Now, let's continue with that. Based on what we said, we can say that a macrostate is what we can observe. Let's see, for instance, a macrostate like this one, we can say that we have 3 molecules on the left and 1 on the right. Now, microstate is what we can't observe. Let's say molecules A, B, C are on the left and D is on the right. This is something we don't observe. And again, the most probable macrostate is the one with the most microstate. Important to remember this. Why is that important? Well, the trick of a statistical mechanics is not to study a single system, but a large ensemble of states. And I want to highlight this word, ensemble, because it refers to a concept which is very important in statistical mechanics. And as we will see later on during the module, we understand macroscopic systems as an ensemble of microscopic states. So let's, for now, keep it with the definition of an ensemble. And we will, don't worry, we will go farther into it as the module goes on. An ensemble is the mental or virtual assembly of all possible microstates for a thermodynamic system. And that's how we describe our macroscopic world, our macroscopic properties, as an ensemble of the microscopic states, all the microscopic states that are possible for that system. So let's continue now with our simple example of the gas. To keep building this into more complicated description and to develop a more mathematical description of the problem that we will use later on during the lectures on statistical mechanics. Let's do it more formal. So if we have this bulb of any temperature that is higher than 0 Kelvin, gas molecules are in constant and random motion. So this is actually the more realistic representation of what we are dealing with. And let me emphasize, it's very important to highlight the word random, because this is why we are using probability, and this is why we are using statistical methods. Now, if we open our valve, we know that this molecule will go on the other side. What we are going to do now is how do we describe mathematically the reasons why these molecules will distribute to both sides. This movement is rapid and random. And again, it's important to emphasize that because we are dealing with randomness of molecules. So let's assume again we have 4 molecules in the system. At time 0, the 4 molecules are in an initial state. So they're all, we said, on the left side. But as time proceeds, other states appear. Now, in how many possible states can the molecules be arranged? We already know at this point, we should know this very well. So let's start with the 4 molecules and keep increasing the number. We said that these are the possibilities or macro states for the case of these molecules. If we look at one in particular, let's choose this one. For this macro state of 3 and 1, we know that there are 4 possible ways of microstates in which the 4 molecules could be in the in which 3 molecules could be in the left-hand bulb and 1 in the right-hand bulb. If we put this in a better, more described way, we already said we would have A, B, C, and D on this side, A, B, D, C, A, C, D, B, B, C, D, A. So these are the 4 possible combinations of these 4 molecules inside this case. So what we have initially were the macrostate. For this macrostate, we have 4 possible microstates. So the number of microstate is a given state. In a given state is a binomial coefficient. Binomial, this funny way of representing a number where it's in parentheses with one number on top of each other and no line in between, this is read as n choose k. And it is defined as n factorial, k factorial, n minus k factorial. Now, factorial is not a surprise. You already know that. If not, let's refresh it. Factorial means the product. For instance, for 4 factorial is 4 times 3 times 2 times 1. Therefore, what these descriptions telling us is that these n choose k is the number of ways in which n, in this case 4, molecules can be arranged with k, in this case 3, of them being chosen to be in the left-hand bulb. Important, we are taking the left-hand bulb as reference. So if 3 are on the left side, we know there are going to be 1 on the right side. So for our case, we have 4 choose 3, which if we develop, we see that is indeed 4 possibilities. We knew it was 4 because we made it by hand as an A, B, C, bar, D, etc. And it was pretty easy. We are dealing with 4 molecules. Imagine when we are dealing with way large number of molecules or particles. It's important to have a more formal mathematical description of the system to go into much more complicated systems. Now, that helps to define something we call multiplicity, that we represent with the letter omega. Indeed, multiplicity is defined as the number of microstates making up a single macrostate. Indeed, it's the number that we just calculated. So if we look at our table, in which we have one possible microstate for the first macrostate of 0, 4, then we go throughout the column, throughout the table from left to right. Our multiplicity, as calculated with the formula that we just learned, would be 1 for the first case, 4 for the second, 6, 4, and 1. These are the multiplicity for each of the 5 macrostates as calculated with the formula that we just learned. Now let's play a little bit with our beloved table that we've been already seeing quite a lot and we are very familiar with. Let's look at it and let's make a funny game with the table. We're going to turn the table upside down like this. So this is the now a new way of looking at the table, a bit funny, but it helps to look at, wow, it looks like some kind of distribution. Indeed, what this is giving us is a distribution of states along the possible macro states. So we have 4 molecules, 5 macrostates, and 16 microstates that are distributed in the way that we just saw. So with that, we can then talk about probability distributions. Here's an example. I show the probability distribution as it looks for the case of 6 molecules. We're starting now to increase the number of molecules. Now that we have a bit more mathematical and formal description of the system, we can start making it a bit more complicated. Well, probability distributions are indeed a graphical way to visualize what the most likely outcomes are by representing the probability of each outcome. And it's important to remember that the sum of probabilities is always 1. So having these probability distributions help us to describe our system. And as we get more complicated, we can see how it's pretty useful to use. So our observable state, based on what we say, are generally the most probable state in that which is observed, and the more ways of making a state, the more probable it becomes. Here we can see on the right how, as we increase the number of molecules from 10 to 20 to 30, the distributions changes toward a more continuous curve, but always keeping it as discrete. Now, remember at this point also what we learned about probability, how we define that, and also what we have learned about multiplicity, and then what we have learned about the number of possible microstates. Now, based on these 3 formulas, we can then define the probability with the following formula, where we are just putting together multiplicity and total number of microstates to define the probability of each macrostate, which is indeed the formula we use to calculate the probability distributions that you see on the right side. So, summarizing what we have seen, we have a system in which we indeed know now that the molecules distribute equally on both sides based on the statistical description that we just made. Remember that the actual observation that we are just describing here is an ensemble of all possible microstates for a thermodynamic system. This can be described as a probability distribution that, as we increase the number of molecules to actual real number, it approximates to a continuous curve, which is the one that we will be describing and looking at throughout the course. Now, the important thing of this probability distribution is that the most probable macrostate, our observation, is the one with the most microstates. This is the core idea from this lecture. We have also learned how to describe more properly both probability and multiplicity by incorporating a mathematical description using the concepts of n choose k, binomial number here for the multiplicity, and also our funny exclamation sign, which is the factorial. With this mathematics, we have now the basics of probability that we need to go further into our problem. So thank you very much, and let's see you in the next lecture.